Reverend Father Kurian John, our special guest and today's keynote speaker of the first session of this faculty development program, Dr. D. Pamu from IIT Guwahati, Dr. P.S. Rao, co-coordinator of this 5 days faculty development program under AICT Atal Academy, entire mechanical department and all the participants present over here. A very good morning to all of you. On behalf of entire CCT family and myself, I welcome you all for this FDP on innovations in manufacturing of novel materials and composite. As already Dr. P.S. Rao have mentioned that the course and detailing of the FDP, the transformations occurring in the energy, automotive, logistics, manufacturing, constructions, and other industries in combination with the evolving industry 4.0 innovations, those drive demand for new materials. The composite materials are of vital importance in today's world because barely any of the material is used in a pure and unalloyed form. The different materials are usually combined to achieve the desirable properties such as high strength and toughness, corrosion resistance, etc. in the final product. The material industry trends range from solution for the sustainability, lightweighting, 3D printing, and surface engineering, as well as in developing the intelligent system, material, nano formulations, and advanced properties by advanced composites with enhanced characteristics. Further, widespread adoption of artificial intelligence and machine learning and data management practice, those we scientists are try to explore and develop novel materials much faster, accelerating time to market from a couple of decades to just a few years. After seeing these various topics, aspects of this field, the topic has been chosen for this faculty development program. I am highly honored to take this opportunity to express my sincere thanks to Dr. D. Pamu from IIT Guwahati to accept our invitation and sparing his valuable time with us. With his lecture, we are going to start our faculty development program, and I am confident that with his excellent record of achievement and expertise in this field will give us knowledge for making aware of technological advances and innovations in manufacturing of novel materials and composites. We are honored to have our executive vice chairman among us who always encourage and advise us to organize this type of webinar, seminar, where we can share and learn many things all together. So your presence is always a moral boost for us, sir. I'm grateful to all distinguished participants to be united for this faculty development program. I would also like to take this opportunity to congratulate Dr. P.S. Rao and the mechanical department to organize this type of FDP. This is the third time they are organizing, where people are sharing many things, they are learning many things, they are adapting, which are really beneficial for their future venture. Once again, I warmly welcome you all this 5 days faculty development program. Thank you.
Yeah, thank you, madam. Thank you very much for giving nice introduction about this FDP. Now, our respected Reverend Honorable Father Executive Vice Chairman, Father John Kurian, to say few words about today's FDP.
Okay. Good morning to one and all of you present online for this FDP program. Respected Dr. Dipali Soren, Principal of CCT, Dr. P.S. Rao, HOD of Mechanical Department, CCT, renowned faculty members of various colleges, IITs and NITs and various colleges from India, research scholars, and all the guests present for this online meeting. It is really great that AICTE is organizing these faculty development programs from time to time. And this time the topic is innovations in manufacturing of novel materials and composites. which is a very relevant topic. And when such trainings are going on, our faculty members come to know about the latest innovations, and through the faculty members, of course, the students, and through the students, of course, the country is going to be benefited by such programs. I am not much into the technical part of the theme of this FDP. I know that I am not into it. I am, of course, I am into academics for quite long year. So just a few points to the faculty members I would like to suggest is, in the past years, it has come it has been known to many of us that the value of the young engineers are gradually going down. I don't know the reason behind it. Maybe you will be better to judge the reasons behind it. But it's a sad fact that engineering profession, I'm not telling it has gone down completely, but somehow it is affected in some fields particularly in India. So we have to really understand and find out how to raise the quality of our engineers. Because I know when I travel, I have traveled in the West, I have traveled in the Middle East. There was a time when Indian engineers had lots of caliber and they had lots of powers. But now what we find is our value has gradually gone down. That should not happen. And the whole thing depends upon our faculty, not only of one college, but all the colleges throughout India. We have to see this is not just a teaching session where you teach and you go, but you have to understand that our children should get or gain lots of practical knowledge. That is very much essential. So whatever you are going to learn and discuss this coming week, I think I have seen the program for these days. So throughout these days, you are going to have lots of training program. Experts in this field are taking the sessions. So whatever we learn, whatever we gain from this FDP program, that should be utilized and brought out in practical to the children. Only then will the idea of AICTE be visualized. Actually, such programs are organized not just for time wasting of time, but it is organized so that we can be beneficial, share the latest inventions and discoveries to our children, so that it can be beneficial for the country, for the child or for the student, and for everyone. So as we go on with the program, let us all decide and take a promise that whatever we learn, it is given back to our children properly in a good way, so that it can be beneficial for everyone in our country and the world. So as you take part, please remember these points to make what you learn a practical thing for your students. So on behalf of our chairman, His Grace Dr. Joseph Dionysius, and the managing committee of the college and all the faculty of the college, I take this time to inaugurate this program. God bless you all. You are leaders, and that leading capacity, whatever you learn, should be shared on with your students, so that they can be young and smart engineers for the world. God bless you all.
Thank you very much for for sharing valuable words about our FTP. So I would like to introduce about our college. Christian College of Engineering and Technology is one of the oldest engineering college in Chhattisgarh. It is established in 1998 with a great vision of late lamented Bishop H.G. Dr. Stephanus Mar Theodosius in 1998. We have very good infrastructure, and we are running UG and PG and PhD courses in our college. We have 4 engineering courses: electronics and telecommunication, electrical engineering, mechanical engineering, and computer science engineering. And along with that, we are also having courses in CAD/CAM robotics, MTech course in CAD/CAM robotics, nanotechnology in the electronics department, and high voltage engineering in electrical engineering department. We are also having PhD in science, maths, and also chemistry and electronics, and in other streams. Our department, mechanical engineering department, came into existence in the year 1998, and the department was accredited, and we have got very good infrastructure, and we received so much of funding from our CG cost, means Chhattisgarh Council of Science and Technology, and also we got research. We are having the tech projects sanctioned by our CSVTU. So we welcome you all once again for this FDP. So now we will be starting with the first session. The session will be taken by Dr. D. Pamu. He is the Associate Professor from IIT Guwahati in Physics Department. He will be delivering us the lecture on the topic which I have scheduled. And thin film oxide materials, fine optical applications, protective layer coatings, CMOS technology, and other electronic communication devices. We grow thin films by sputtering, laser ablation, and thermal evaporation methods, and optimize the processing parameters to achieve low temperature crystallinity, uniform microstructure, and best electrical properties. So this is the area of the research of the SAR, and we are nice to have such a great expert amongst us. And I hope this session will be very much useful and helpful for us to learn and equip ourselves in our field. So I hand over to Dr. D. Pamu.
Yeah, very good morning to you all. Thank you, Dr. Srinivas Rao and your management for inviting me. And can you hear me right? I am clear, right?
Yes, sir. Yes, sir.
Yeah. So at any point of time, if you have any queries, you can please ask, or I would like to go as slow as possible because this is a new technique or the new technology I'm introducing to you. So if you have any queries at any point of time, let me know. Or if you want to ask question, you can, I don't know what is the protocol you are following, but still you can ask me. I have no issue to answer. So I welcome you. So the screen that is shared, the picture there is our campus, beautiful campus, where you will see a lot of greenery. When you get a time, visit our campus. You are also welcome to visit my lab. So now today I am going to introduce you a technology that is called the thin film technology. Most of you would have heard about it, or if you are planning to do research, probably you will have to learn about these things carefully because we are most of the times we are trying to reduce the device size and integrate the technology or minimize the device size, enhance the performance. That is what is our basic idea when we talk about a thin film technology. Of course, you may ask that I am a mechanical engineer, why do I need it? Actually, thin film technology is more relevant in mechanical engineering devices than any other. Of course, electronics, we cannot particularly say that it is not required to my area, it's not my interest. Anything you name about, you will know that there is a thin film technology. I will try to show you the background, all that. So before I talk a lot about thin film technology, I would like to introduce what do you mean by thin film. If you say that thin film, suppose thin film is a three-dimensional solid. That means, I am taking a substrate. Are you able to see my screen? I am writing. You are able to see my screen, right? I am writing. I have drawn a picture. So onto which I am trying to deposit a film. And see, this is my substrate length and this is my substrate width. This is L and this is width. And this thickness, what we have shown here is much smaller than the other two dimensions. So that is what is called the thin film. So thin film is nothing but a three-dimensional solid, and one of the dimensions, which is called the thickness, is much smaller than the other two dimensions. And then thin films range in thickness. What do I mean by that? See, if I go to an electrical or electronics engineer, if I say that, I can give you 100 nanometers, he will say 100 nanometers. Why do I need 100 nanometers? For me, 2-3 nanometers will do. But the same thing, I go to a mechanical engineer and say, no, what is 100 nanometers? At least we need a couple of microns. That is what is the requirement of each field that we work on. So the thickness, when I say a thin film or thick film, it all depends on the area of my research. That is what we need to keep in mind. Okay, so now when we say thin films, where these thin films are being used, you see that the very first one is the industrial coating, where you need to have a protective layers in every case. Any device you name it, unless you have a coating, protective layer, then the device will not function for a long time. In the optical coatings, you see that these are the different percentages of thin film devices that are or the thin film coatings that are being used in all these things. You see that it is there in the MEMS, nanotechnology, ceramics, biomedical research, laser, instrumentation, plastics, flat display panels. Now you see the revolution in the LCD, LED TVs and quantum LEDs. Metallurgy, then semiconductor, catalysis, environmental, disk drives, ink, decorative coatings, abrasive coatings. In many areas, in every aspect of it, the thin film technology is very much evident. That is what I would like to say. So thin film technology is not maybe little new to you people, but this technology is very much part of all the areas of our day-to-day devices, and also that they are used in the advanced devices and advanced technologies. Can you see my screen?
Yes, sir. Yes, sir.
You are able to see my writings also, right?
Yes, sir. Yes.
Okay, thank you. So I'll move on then. I will just give you a brief, being defined what is meant by a thin film, then their application, the percentages of application in various sectors. Then I will move little, I will try to show you various devices that are made with thin films. Then I will go on to the thin film technology. How do you, having seen many applications, how do we make a thin film? And what are the techniques available? How do I, if I want to select or start a thin film instrument, how do I do? What are the requirements? All that I will talk about. So here if you see materials, see mechanical devices are there, mobile equipment is there, environmental, and then environmental infrastructure. The environmental cautious cars means now we are talking about the battery vehicles, all that. In all these cases, you see that thin film microfabrication is being done, signal processing, structural wave. In every case, the devices are very small, but their performance is much higher. Earlier, we know that, right? If you have very old TV in your home, you will see that the TV is very bulky. The very first TV, when now in my village somebody bought it, 5 people used to lift the TV, big TV. Now you know that we are having LCD screens which are very simple. And now we are also talking about foldable electronics. That means flexible electronics. You will be able to fold your TV and take it. That is what are the days that are ahead of us. So in all these cases, what is happening is that you name it as a infrared device, silicon industry. If you look at sensors, biology, the piezoelectric sensor, magnetic dielectric materials, inkjet heads, anything you name about pressure sensors, in all the cases, these thin films are much effective in their performance, also much lighter in weight. That is what is the advantage. Earlier we used to feel stronger, thicker is the stronger. If you look at your old house, the wall will be very thick. But now you see that the walls of the building are very light. But at the same time, the strength of the building is not compromised. So what had happened in between? So there are many other techniques available in order to build a smart, materials, smart devices, smart technologies, which will really enhance the technology and performance. For example, thin film MEMS technology, which are very simple. They require very, very eco-friendly, very convenient. They are much easy to use, and they are very safe devices. That's what microelectrical mechanical systems. So you can see the very smart devices that are possible. And then when you talk about thin film technology, MEMS technology, you always talk about the safety. Also, that any device you talk about, the mechanical stability and strength of the device is very much important. That we will show you in the afternoon. Even though we talk a lot in the technological aspect, in every aspect, the mechanical stability of the device and the strength of the device are very much important, and we will show you in some of the applications when we discuss in the afternoon. So you look at smartphones. Earlier in 2004, when I have my first mobile, it's very bulky, and it's very the functionality of the mobile is very poor. Now you see sorry. So you see now you have a very efficient devices possible, and the technology is growing day by day. And you know that, right? In the statistics, if you look at the poor people, they may not have the toilet in their home, but people are having at least one phone in the home. So people prefer even the mobile or the communication than their regular comfort. That's what is the demand from the people. That way you can look at the very advanced devices, infrared sensing. Here you see thermal imager optics. You can see, then the new interfaces are coming. Humidity sensor, which are very small. You can see the sound quality using the Novell's microphones. So the sound quality will be much better. And you see the MEMS oscillator here. You see that any device that you are naming, the thickness of the device is becoming smaller. The size of the device is becoming smaller. At the same time, the performance of the device is becoming better. That is what You see that these are all thin film devices made, and in the wireless communication, without this things, you will not be able to have a communication between the people. That's what you will see. And it's not only in the great electronics we look at, in every case. For example, you take about a simple lace packet where there is a vacuum technology is there. Why the lace are very fresh? Because there is a vacuum inside, and also that the surface of the layer, this packet, is coated with a plastic thin film, so that it looks very glancing. That is where it is very attractive. The same lace, aloo chips, if there somebody sells by roadside, you will not buy, but you look at the packing, you will nicely buy it. Even the pedigree, everything that you talk about, you see that how they are thin layers of sheets, how they are making it as a rolls, and these are all used for this kind of decorative coatings. You name, these are all cosmetic, and these are also silver. These are the gold wires where people will be using for the inter device connections, with the wire bond or all that, which are essential. So you can make very thin ones which are useful for various applications, and thin film technology is there here also. And then you look at for example, aeroplane industry or the aviation industry. You see that the plane will go through the very robust conditions, but you see that these areas, the plane surface is coated with a super hard coatings, irrespective of the environment it is passing through. You will see that they have a safety coating, so that the lifetime of the uh, device is extended. And you see the turbines, and you see the any device you name it, it's a metal, but to extend the life of this metal, there is a carbon coatings. Various coatings can be done, and the thin film devices are also there at the space applications, where or the communication devices, where that earlier our TVs, we used to align into a particular direction in order to get a picture. Even in this case also, cell phone towers, sometimes you might be very close to cell phone tower, but you will not be getting the signal. What is the reason? Is that you will the antenna would have been misaligned, but with the thin film devices, they make a the filters, tunable filters, where if you apply few volts of electric field, then what happens, you will be able to tune the direction of the antenna, so that you will get a better signal. That they do it very frequently, and there you use. And also here, if you look at different types of nanoparticles, depending on the size, the color of the color of the material changes. Even the same material, but depending on the particle size, the color also changes. So you can play with various parameters in order to get a device. And another thing, now the recent trend is that thin flexible printed batteries. These are all very much required now. You know that, right? In eyes they put a special lens. These are all thin film devices. So smartphone, and then the wearable devices you talk about, RFID, smart cards, everything you mention name, there is a, you see that there is a thin film technology that is being involved. And how do you do? See, these are medical devices. How do you do them? How do you fabricate them? So how it is possible that we will be able to do such a thin devices with a better efficiency? How we will be able to do, we'll try to understand. And this is called the flexible devices is another field that is coming up, and also the organic electronics. Thin film transistors, solar cell, batteries, fuel cell. In every case, you will see that the smart devices are being fabricated. Of course, in this case, it is still thin film technology, but a different thin film method is being used to deposit thin films using to fabricate this kind of thin films. And also some of the flexible electronics, if you see here, you will know that how this is a very flexible device. You see that this is also, you see that the layer by layer you put it up and then fix them. That is how you will see this is the thin film energy harvester. You see that how the LED volatile LED devices they have fabricated, you see on the surface. So here again, this is again a flexible energy harvester where you apply the stress, and these are the IDEs, that is interdistricated electrodes, which are being there, and they will try to, when you apply the stress, you will get the voltage done, and that's how the flexible electronic industry is booming up day by day because of the excellent properties. Also, you explore the smart materials for this kind of applications. And again, thin film solar modules, you know that now the electricity is a basic problem, and solar energy is abundantly available. So how do we make use of them? And we will be able to make solar panels, and we'll be able to generate. And earlier this cost used to be very high. Now the cost of that also is coming down drastically because of the improvement and enhancement in the properties of the materials, as well as that results in the solar panels, and the efficiency ultimately increases. That's what is happening. Then if you look at we have looked at lot of applications, all that. Now if you look at the market, global market, it's day by day, it's not one area. The penetration of electronic intelligence in physical objects itself is a 100 billion market. It's these statistics are about 2012 statistics I am showing, but now it would have been double every 5 years. When you look at the electronic devices, their usage is becoming double in every 5 years. That means you can understand the importance and the growth of that. If you look at even cloth industry, you may ask, sir, where the cloth industry is required. Now you look at in the places where it is very hot, we are afraid that UV rays are coming, and you will see that people are putting a titanium layer on the top of clothes, shirts. Then the titanium layer will absorb the UV rays, and then it will protect you, and it also will not let the dust to fall on. You can just shake it and the dust goes off. You will be able to reuse it without washing. That is how different technologies are being used. The car industry and then electronic industry, you see that 2.3 billion, that is in that range. You see that every device you name, and disposable various items, even in that time itself, 2001, 5 to 10 trillion market. You will see that the market gap is increasing day by day, and if you can produce an intelligent device, then the market is always there to promote. But what is the thing is that in all these things, what is making is that the thin film devices are crucial, whether you name it in the consumer electronics or cosmetics, anywhere these things have come up. But how do we understand these things? That is what we will like to look at as we go on. So these are all only few things I have just mentioned, but my purpose is not to just advertise about thin films, but their applications. But my purpose is to look after how to make you understand what is the thin film, how do you do the coatings, all that. That's what we will move on. So now, as I told you, the definition of very definition of thin film. But now, how do we do thin films? That is what is important. Why thin films are very much important is that, thin films are deposited onto a bulk material. That means I have to deposit this is my substrate or the glass slide onto which I will put a layer of a thin film. Suppose this is a, if I say just a silicon substrate onto which I am putting a TA board to achieve a. So suppose if I am having a titanium TaO2 substrate, suppose, onto which if I use, since it is already TaO2 substrate, if I use this one bulk substrate, it will not give me a good response. But the moment I put a nano layer of TaO2 again, this will give me a better performance. That is what is the advantage of thin film. That's what I am saying. Solid body which exhibits significantly lower geometrical extension in one dimension than remaining two spatial dimensions. That's what I told you about thin film. The properties of the film or coating have have to differ significantly from the bulk. That means even if I have TaO2 substrate, if I use it as a device, it doesn't function. But on top of TaO2, if I put 100 nanometers of TaO2 layer, then it gives me a better response. That is what is the advantage with the TaO2 thin film. Also, that whenever you want to deposit a thin film, you always have to have a substrate, some base to test your material. If I want to do for mechanical testing, I will deposit on a titanium substrate, any other material I want to do, because my base also is very much important. That is what you see. As I was telling you, how do I distinguish between a thin film and thick film? As I told you already, if I talk to a mechanical engineer, for him 100 nanometers is not a film coating at all. But if I talk to an electronics engineer, for him 100 nanometers is too much. And we work both with the mechanical people as well as the electronics engineers, where electronics engineers only require 5 nanometers of thin film. But we are also working with the mechanical engineering people, and where we have to give them at least above micron size. That is what. So thin film and thick film, how do I distinguish? The limit between thin film and thick film we cannot generally do, but if we look at the textbook definition, even in the textbook, if the author is from mechanical background, for him less than a micron is a thin film. But if the electronics engineer, is the author of the book, then he will say, 100 nanometers is too thick for him. It all depends. But generally, as a good student of thin film technology, how do I understand? Basically, a thin film can be considered as the thin when its properties are significantly different from the bulk counterpart of it. That is what. And when we ask the next question, how come these thin films are why they are same material when it is in the thick state, bulk state, it doesn't exhibit good properties. But when I make it a thin film, how come it is giving a very good properties? Then the reason is that the surface to volume ratio will be higher as you make a thinner and thinner. That these properties will enhance the response of the thin film. That's what we need to understand. Is it okay? Are you able to understand what I am saying?
Yes, sir.
Okay, thank you. So now we will move on further. So there are different classes of thin film deposition methods are available. I would like to introduce some of them. And since we cannot in 1.5 hour time, I will not be able to talk about all of them, but few of them we will try to discuss. There are different types of these thin film methods or deposition methods are classified into different classes. One is called the gaseous solution state, another is called the molten or semi-molten state. In the gaseous state, These are all the called techniques. CVD, that is chemical vapor deposition technique, PVD, physical vapor deposition technique, and IBAD, ion acetate deposition technique. In the solution state, you have a chemical solution deposition method, electrochemical deposition method, sol gel methods. Of course, this is a broad classification I am telling. Now, if you look at the literature, you will find a large number of techniques are available within each this thing. And molten and semi-molten, you will see, laser, thermal spraying, welding. These are all mechanical engineers. Mostly they dependent on that. We will see these are the general classification. But here the most prominent techniques or what I have shown you earlier, different applications are done by these gaseous state methods. Why these gaseous state methods are very important? Why not these things? If you look at gaseous state methods are the coatings quality of the deposition of the film. The quality of the film will be much better in the case of a gaseous state compared to solution state or a molten or semi-molten state. That is where my focus today will be on gaseous state methods. We will look at it. So these are all basically called the PVD and CVD methods. PVD is nothing but a physical vapor deposition method where I'll try to physically evaporate a material or use a physical principle to make a thin film of it. And CVD, that is a chemical vapor deposition method. I start with the chemical of different reagents and try to produce a film. So in this slide, I will be explaining both how these techniques are different from one another. I will just try to explain and then I will move on to further PVD techniques. So in the case of CVD, how do we start? In the case of CVD also, we have varieties of techniques, which is called thermal chemical vapor deposition techniques, light CVD, plasma CVD, low pressure CVD, high pressure CVD, atmospheric CVD, all that it is there. So what do I mean by PVD or the CVD? CVD is nothing but a chemical vapor deposition. How do you do in the film in the chemical vapor deposition? Let us see here an example here. Suppose I want to make a titanium nitride using a CVD. That is the chemical vapor deposition method. So what I do, I'll take a material gas intake and then, so this is my chamber, suppose. This is my substrate onto which I want to put a titanium nitride coating here. But underneath the substrate, there is a heater which is heated at a very high temperature. Why this is required? Because the material gas that is coming inside the chamber, they have to break the bonds. For example, to deposit a titanium nitride, I am starting with my initial reagents are titanium chlorate, nitrogen and hydrogen. So when I heat it here onto the substrate, I will get a titanium nitride and HCl. This HCl is a byproduct. If I remove the byproduct, my film is deposited here, titanium nitride. That is what is called the chemical vapor deposition method. In the chemical vapor deposition method, either you start with a liquid or a gas form, which are volatile. What do we mean by volatile? These gases will be the bonds between these molecules like TaCl4, that is the titanium chlorate. The bonds will be broken when I heat this TaCl4 at a particular temperature. Then I will be able to produce a titanium nitride and hydrogen fluoride. That is how I will be able to do. So in this case, CVD, I will always start with a volatile, gases or solutions. And in the case of PVD, what we do? In the case of PVD also, we have varieties of techniques. What we do in the case of PVD, that is a physical vapor deposition, here we start with a solid material. Suppose if I want to, deposit TaO2. I start with the TaO2 beginning and I take the TaO2 here and I will vaporize the TaO2 molecules here. And this vapor, I will make sure that it is falling onto the substrate again, so that I will be able to make a TaO2 thin film there. Okay, so in the case of PVD, I'll start with the solid. That solid I will again vaporize it, bring it to the gaseous state, and then again I make it a solid. That is what is the difference between a PVD and CVD. Am I clear? If you have any doubt, please ask me. If I am not clear, you please stop me and ask me. Okay, so how do I distinguish between factors that distinguish between PVD and CVD? How do I distinguish? What are the fundamental differences between PVD and CVD? If we see here, in the case of PVD, we start with a solid. For example, I want to deposit a barium titanate. I want to make an energy harvester, suppose. I start with the PVD. That means I start with the solid only. Then what I'll do is I will evaporate it. I'll bring it to gaseous state, and then I'll make sure that it will be solid again onto the substrate. But in the case of CVD, you start with the gaseous precursors. That means you will start, either a liquid or gases. You start the composition of that, and then you will move on. The physical mechanisms in the case of a PVD, physical mechanism, that is, you thermally evaporate. That means you heat the material and vaporize it. Make sure that you are making a thin film. But in the case of CVD, you are starting with the gases. Already you are starting with the gases. The bonds between the gases, you are breaking them and making a thin film of it. A reduced pressure environment through which gaseous species are transported. That means what? In the case of PVD, you will have a vacuum. Of course, in the case of CVD also, you will have the vacuum. But one basic difference between a PVD and CVD we should remember. In the case of CVD, your substrate is the heart here, because onto the substrate only, underneath the substrate you have a heater here. So the gases are coming here, they are falling onto the substrate where the substrate is heated, and these gas molecules decompose here. That's what we have seen, right? Titanium fluoride plus nitrogen and hydrogen. How are you doing it? Titanium nitrate and HCl. That's what you are seeing here. So same way, in the case of PVD, it is not that. These are the fundamental differences you need to remember when we talk about a PVD and CVD. Okay, and then I will just move on. Of course, how these things will happen, let me put up here. So as I already told you, the differences between PVD and CVD, and what are the fundamental steps involved, I will just put up here. So what are the fundamental steps involved in the PVD or CVD? So what we do, we first start with the vapor phase generation from coating material. That means, suppose if I am doing a PVD, what I do, I want to deposit TaO2. So I will heat the material physically, using some of the methods that I will come to you. I will vaporize it here. These vapors, I make sure that they fall onto the substrate. You may ask a question, sir, how these vapors will fall onto the substrate? What we do, there is a vacuum chamber here. This is a chamber here. In the chamber, there is a vacuum created initially, like something like 10 power minus 6 torr pressure is created. Then onto which inside the vacuum I am doing it, so that these vapor molecules are free to travel. That is what you need to remember. So that these vapors, you may say that only onto the substrate they will deposit. No, they may deposit onto the container walls also. But still, the major deposition occurs here, because if you study the kinetics of it, you will be able to get it clearly. So in the case of PVD, what you do, you either evaporate, sputter, arc evaporation, chemical vapor gases. Whatever it is, this is the general technique. That means you start with the vapor phase generation. Your starting material may be solid or gas or liquid. Whatever it is, you will make it as a vapor. Then transfer of the vapor phase from the source to the substrate by line of sight. This is what I told you. So you are, in the case of CVD, you are doing the entire reaction on the you are doing entire reaction on the substrate itself. So here I have a heater. So the entire reaction will happen. In the case of PVD, because you are under vacuum, you are able to do that. See, line of sight, molecular flow, vaporization by creating a plasma. All this comes here. I will come to you to that point later, little later. And then deposition and film growth on substrate. So you start with the solid, you vaporize the solid, and that solid you make sure that it will fall onto the substrate. What are the means? Line of sight. What do I mean by line of sight? I create a vacuum so that in the vacuum, since there is a large mean free path, the atoms can travel and fall onto the substrate. That is what is the thing. And thirdly, the moment atoms are coming and falling onto the substrate, you are able to grow a thin film here. That is what you are able to do that. These steps can be independent, or sometimes these are the fundamental things. Sometimes you may have a so these steps are fundamental steps either for PVD or CVD. So that is what I would like to say. So these are the fundamental differences between a PVD and CVD. I will move on as we go further. Okay. So now, am I clear up to this point? Do you have any queries to ask?
No, sir, clear.
Clear, right? Okay. Suppose I am new to the thin film field, but due to the demand of the technologies, all that, I want to start a thin film deposition technique. I want to learn one technique, but I have no idea how to choose what kind of, whether I should go for CVD or I should go for PVD. And in CVD also there are varieties of techniques. In PVD also there are varieties of techniques. How do I choose a technique first of all, which is cost effective? How can I go ahead? That question always comes with the for the beginner. In that case, these are some of the selection criteria. But because in the case of CVD, you don't need to worry much about it, because in the case of CVD, as long as if the parent material or the composition, like when we have seen in the case of titanium nitride, as long as you have the precursor gases are available or liquids are available, it's fine for you. But in the case of PVD, where the most commercial techniques are the PVD, of course CVD also I'm not underestimating, but most mechanical in this. So the moment you talk about these things, you have to have an understanding. So if you want to, what is the criteria to choose the type of material to be deposited? Suppose if your material is a very high temperature material, high melting point material, then CVD may not be a good option. Or you need to choose, if you are using, if you are going with for example, this kind of a deposition, like barium 0.5, strontium 0.5, and TaO2, TaO3, and then into this you want to have a 2-8% of magnesium oxide, so magnesium titanate. Such a complex composition is required. In that case, to do this kind of material deposition, I have to have a special understanding about the technique also. I cannot, so okay, I have a thermal evaporation system in my lab, so I can use it. You cannot use it because the composition is very critical. If the composition is not coming properly, then you will not be able to get a very good quality thin film. That case, you will have to choose a proper technique. That is what, and the rate of deposition. Suppose, what is the meaning of it? For example, we do some bio coatings. It takes almost 30 hours to deposit a 1 micron thin film, because the nature of the material is like that. We will not be able to get a more deposition. Sometimes industry needs suppose 30 micron thickness. The industry may not want to do a 30 micron for maybe 3-4 hour days continuously. Industry may not want to do that. So whether my rate of deposition is important, or rate of deposition means how fastly I will deposit the thin film. And limitation imposed by the substrate. For example, if I have a very high melting material and it needs a very high substrate heating to get a crystalline film. When I say a crystalline film, probably you will understand. Crystallinity means what? It is the periodic arrangement of atoms. If they are not periodically arranged onto the substrate, the film may not exhibit a very good response. That is what we should realize. So that is where you need to look at. Sometimes what happens is that in the case of CVD, sometimes if you have to go very high temperatures, you may have to come with the CVD, or other way around also. So depending on that, you need to also. All the time you may not have a flat substrate to deposit a film. Suppose when you do industrial coatings, all the time surface may not be flat. There will be curvature. How do you do? That also you need to look at. Adhesion of the deposition to the substrate. Sometimes what happens is I deposit a film onto the substrate. But if it doesn't stick properly, what happens? The film gets peeled off. Then it's not good for the application, right? In that case, I have to see how the film is, whether it is attaching to the substrate or not properly. And also throwing power. That means if I am using RF power sputtering, then how much of power I can do, because that decides the thickness of the film, how fast I can deposit a film. Sometimes the uniformity of the thickness is very much important. When I deposit a film, it has to be uniformly distributed. Suppose I say 100 nanometer film should be deposited uniformly. That means the film has to be deposited uniformly across the substrate. Anywhere I measure the thickness, the film thickness has to be exactly 100 nanometers. It has to be uniform thickness. Otherwise, it's not good. And also purity of the coating materials. Sometimes if you need very ultra high purity, that case maybe CVD may be better, because the purity of the gases may be higher. Or if you can make a bulk material with high purity, you can do also. Equipment requirements and their availability also is important. It's not that suppose I have only sputtering technique and I have to do some very complex deposition possible. Then I need to carefully study and understand, with this I'll be able to do it or not. And the cost also. See, all the PVD techniques are initial cost you need to put up, but all the CVD techniques, they are slightly cost effective. But your consumables is always more, you are costly in the case of CVD. Ecological considerations. That means, see, for example, when I shown you titanium nitride coating, TiCl4 plus hydrogen and hydrogen, and then you are having a titanium nitride plus HCl. So your HCl is always a byproduct. This always go into the environment. So sometimes when you do industrial coatings and all, they will look forward. Is there any harmful gases are coming? How do you deal with them? You have to be careful. And abundance of the deposition material also important. Otherwise, to buying the material itself, you will invest a lot of money. So these are the some of the important techniques, important things that you need to keep in mind when you want to go for a thin film deposition, and what kind of technique you want to do, what are your requirements. Because you suppose you have a project, it is very easy that without knowing also, if I tell the vendor, he will be able to give the deposition. But the problem is, the moment he knows that vendor knows that you don't know much, then he will cheat. First thing. Secondly is that the vendor also will ask 100 questions. The moment you say that I need a thin film system, he will ask whether you need a DC sputtering, you need a RF sputtering, you need a thermal evaporation, or you need a. If you say CVD, whether you need a APCVD, LPCVD, PECVD, all these many questions they will ask. So unless we are aware of these things, we will not be able to choose or establish a good facility in our lab. That is what you need to keep in mind. So material compatibility, you need to look at all those things you have to see. So there are advantages are there, you need to look at. PVD materials are sometimes PVD coatings are much better compared to other things. You will get good finishing, all that. But there are also disadvantages. What is the disadvantage is that here you need to learn about the each technique very carefully, because when you do PVD techniques, you need to learn about a vacuum and the particular technique. Like if I am doing a sputtering, I need to learn about the sputtering. I need to learn about the substrate heating. I need to learn about the biasing. All that, many things I need to understand. And you will be using gas, high voltage, and the 2-3 gases. Sometimes you will deal with very high power supplies, and also there is a plasma in between. If you are not careful, then these are all very dangerous. So you have to be expert. And also that whenever you talk about PVD techniques, they are costly. Initial investment is more, but later the maintenance will be less. So that is what you need to choose. So with that, I will move on to the CVD techniques, and finally I will move on to the PVD techniques. So giving a brief introduction about CVD techniques or PVD techniques, how to distinguish them, how to identify them. Then I will try to explain a few CVD techniques. Then I will move on to the PVD techniques. When I say that CVD techniques, as I already told you, deliver and meter the reactant and the diluted gases into the reactant. These are the fundamental steps in the case of CVD. I have already explained to you. These are the 3 fundamental steps you need to remember in the case of CVD. So what you do, so I have a CVD chamber. Suppose this is a CVD chamber. What I do, if I want to do a reaction, I need to carefully introduce the gas controlled manner. That's what. So there is a reactor. That means I am heating my but there is a heater here, and I am top of it. My substrate is here. My substrate I will heat, and the gas molecules will fall here, and they will get decomposed. Supply heat to the substrate so that the reaction and deposition can proceed efficiently. That is what you do here. And remove the byproduct gases. As I have shown you, titanium nitride plus hydrogen chloride, how you have to remove the byproduct so that the titanium nitride remains in the substrate. Otherwise, this HCl can etch off the titanium nitride also. That is what happens. You need to be careful. So this is the general principle that I would like to put it up. But how the CVD happens, I will just show you a small animation here. Maybe it might not allow me straight away. I will just do it 1 second. So 1 second. I will just show you. I have a small video of it. I will just try to show you the. Just give me a moment, because this video doesn't work with the tablet, so I have to remove the tablet. So you can see how the film is deposited in the case of a CVD. See, the gases are coming here, you see, whatever gases, and there is a pump here to create a vacuum, and there is a substrate here which is heated up here. See, diffusion of precursors is occurring here, and you see they are trying to form a layer of it. Surface diffusion is happening here on the surface. Sorry. So you have created a vacuum using the pump. The gas molecules are coming. The substrate is heated here, and they will fall onto the substrate, and the reaction is taking place. So this is how the general deposition process continues. I will move on. So here, so there are different types of reactors are there, which are called, based on the chamber pressure, you will call them, LPCVD, or LPCVD means low pressure CVD. Based on if the chamber is pressure is high, it is called the atmospheric pressure CVD. All that, these are all different general principles that we need to understand when we talk about CVD techniques. So here, there are reactor types. There are this is important. If you understand this, rest is very easy for us. So you see low pressure CVD, plasma enhanced CVD. So if your pressure is higher, atmospheric pressure, then mass transport is limited, comes here. What is the mass transport here? You see that, you have a either cold wall or a hot wall. Cold wall means what? So your heater is, suppose this is my chamber and my heater is inside, and there my substrate is there. Hot wall is what? I am winding my heater on the container. That's where is called the cold wall or hot wall. If the mass transport occurs if pressure and temperature are high, and surface reaction will occur when pressure and temperature are low. That is where I am telling. If you are working at high pressures, that is called a APCVD. LPCVD means what? You will have a surface reaction, limited reaction will occur. If you are having a cold wall, no reaction on the wall will occur. Difficult to control the real temperature inside. That is also problem is there. If you have hot wall, you will have a lot of contamination on the surface itself. You need to really clean the substrate continuously. That's what. So in the case of low pressure CVD, as I told you, the heating is important. Zone 1, zone 2, zone 3. Whatever is the length of your wafer, up to that length you have to have the heater. So your gas molecules comes in. Here the reaction take place, and you have the heaters both the sides. You see that, and then the film will be deposited onto this. These are the film, and the exhaust gas is taking place. That is what happens in the low pressure CVD. So what is the advantage? All that I have already discussed. So here very easy to do. It's very fast deposition occurs. Of course, depending on your requirements, you can tune with the low pressure CVD that I will see. What are the advantages here? You can have a faster growth compared to PVD. Less auto doping means impurities. Little dilute gases are required because you are sending them carefully. Lower gas consumption because you are using a gas controlling agents. Fewer byproducts. That's where you will be able to get a good quality film. But line of sight is there little less here, and poor step coverage and shadowing also will occur in the case of LPCVD. So let us move on to the plasma enhanced CVD. As I told you, maybe if I show you the video, you will understand much better. I will try to show you the video. So I think again I need to explain. If I show you the video, probably it will be much clearer to you. Then it's easy to tell me the. So plasma enhancer CVD I am trying to put up here. You please have a look at here how the plasma enhancer CVD occurs here. So in this case, see this is the system, how the PECVD looks like. See, the plasma is created here. That's where that pink color is coming, and the gas molecules are coming. Now the pink color has been changed. You see that? See, gas molecules. There is a breaking of the bonds between the gas molecules are occurring. You see that here. See, and the atoms are depositing onto the substrate. And when you heat the substrate, they are trying to arrange themselves periodically, because the substrate is heated at the temperature. You see that there is a nice growth is forming. And again, the plasma is created here. You see that the layer is forming, thicker layer is forming, and you see how the atoms are falling onto the substrate. So here, what is the need of plasma? If you ask a simple question, the simple answer is that the plasma, sometimes what happens is you have to heat at a very high temperature. So then your deposition may not allow, your substrate may not allow, because your substrate melt at high temperatures. So that way what they do is they will employ the plasma to break the bonds between the molecules. That is what happens in the case of a plasma enhancer series. So I use plasma in order to break the bonds between the molecules. That is what is the plasma enhanced CVD. As I told you here, just a second, let me. So in order to break the bonds between the molecules, you are using the plasma to reduce the temperature, crossing temperature, and the bonds between the molecules are, as you have seen in the video, they can be easily broken nicely, so that you will not have a much disturbance. That is what happens here. Then you may ask questions, sir, how do I create a plasma? So to create a plasma, what you need to have two electrodes. Substrate is one your electrode and top one electrode. You apply the potential between them by applying the RF power and send the gas. So the gas get ionized, and then you will have the ions. These ions will break the bonds between the molecules, as it is written here, shown here, so that they will try to create a plasma, and this plasma will interact with the gas molecules that you are introducing, and they will try to create a film here onto the substrate. So, and here, when this plasma enhancer CVD is required, when low temperature is required, and it gets a very good quality film that you need to look forward. And that's how, if you want to have very high density plasma, then this is the best way you to do that. And also that some of the coatings can be done very but effectively at low temperatures compared to other techniques. For example, if you want to have a dense SiO2 at low temperature 150 degrees C, it's not possible with any other method, only with the PECVD it is possible. Like that. So depending on the nature of the application and the material that I am using, you have to choose the particular material. So what plasma enhancer plasma will do, it will enhance the higher reactivity can use at lower temperatures and low pressures. Lower pressure means you will have a very uniform grain growth and a good quality thin film. And the plasma, all the details I have just given here. You can see here what are the parameters you can play with. You can play with the RF power. You can play with the pressure that you have applied. All that. So you can see that you can play with the pressure, and you see that the pressure changes the energy of the ions reaching the electrodes. Pressure can change the deposition rate. If you work at low pressure, you will have low rate of deposition. If you work at high pressure, you will have high rate of deposition. Increase in
Excuse me,
pressure.
sir.
Yeah.
Your screen is not visible, sir. Please check once.
Oh, not visible.
Yes, sir. Yes, sir. Now visible, sir.
Visible?
Yes, sir.
Yeah.
Yes, sir.
Can you see now?
Yes, sir. Thank you.
Yeah. Okay. Thank you. Because this video, no, I have to go away from the presentation mode in order to play the video. Okay. So power you can play with, frequency you can play with. That is one. Another thing is that you can also do a photo-assisted CVD. What do I mean by photo-assisted CVD? I will use the laser in order to break the, or I will use the light in order to break the bonds between the molecules. And these are all called the pyrolytic. Pyrolytic means what? You will heat the gas molecules so that the bonds between them will break. Or photolytic. You will, here in the case of pyrolytic, you will heat the substrate to enhance the reaction. In the pyrolytic, you will use the light to break the bonds between them. That is what will happen. And you can use the video, UV radiation possible. In the case of pyrolytic, you are heating the substrate here and you are breaking the bonds. You are using the laser. And in the case of photolytic, you are using the light to break the bonds between them. So you can use low pressure CVD, high pressure CVD, atmospheric pressure CVD, plasma enhancer CVD, or a photo assisted CVD to make the thing. And another one is called the MOCVD. What do I mean by MOCVD here? Here you will use the organometallic vapor phase epitaxy. Epitaxy I will come little later. What do you mean by epitaxy is that you are making the substrate or the atoms to sit one top of the other. That is called the epitaxial films actually. So why this MOCVD is very popular is that molecular this metal organometallic components are very volatile at very low temperature. So that's where MOCVD is very popular. Suppose if I want to deposit a gallium thin film, it's very easy if I start with a trimethyl gallium. What is the advantage here? Volatile at relatively low temperatures. There is no troublesome liquid so that the deposition will occur much faster, and there is no carbon, but there is a little bit of carbon contamination because in this trimethyl gallium there is a carbon. So, but however, you will be able to eliminate that. Since all the constituents are in vapor phase, precise electronic control of control flow of gas is very much easy to do that. And this is the best method to deposit a gallium thin film. So depending on the nature of the film, application of the film, you will have a very special deposition techniques possible. Is it fine? So with that, I will close with the CVD. Now I will move on to PVD. So whenever I talk about PVD, physical vapor deposition method, one thing that you should remember is that you always have to have a vacuum. So for that, this is the overview of the vacuum system that I am showing here. What is the need of a vacuum here? The vacuum reduces the particle density so that you will have a large mean free path. And it will reduce the collision, it will reduce the contaminants, and also it will give you a good quality thin film. That is where the vacuum is required in the case of a physical vapor deposition techniques. And then the first one is called the thermal evaporation or the physical vapor deposition. Why this physical vapor deposition is important here? See, this is the system that I have used as a student, way back 2004. You see that this is the system I have used. And what do you do? Suppose if I want to deposit aluminum, I will put aluminum onto this, you know, filament, and then I heat the filament resistively, so that the moment it is become red hot, I stop heating it, so that the film will be deposited onto the substrate. Here, what is the advantage? In a reasonably high vacuum, the material atoms fly to the target. You can increase the distance more. Source material is coated onto the target surface very easily. What are the basic steps involved here? Again, your source material, you start with aluminum, you make it into gaseous state by heating it here, and then transport the source atom to the substrate where I am fixing here, and deposit the atoms onto the substrate. That is what you see here. So very easy to do that. You have a varieties of techniques possible. Let us see how the thermal evaporation is happening. Here you see you are heating the, if I am starting with this kind of material, I am heating it thermally. You see it is melting. Now it is slowly getting evaporated. You see how the atoms are depositing. That's what you see here. And there is another video you would like to see. How the depending on the nature of your powder, your initial material, you may have to use different varieties of boards here. You see they are thermally evaporating, so they are creating the pressure here initially in the system. Now once the pressure is reached, now they are applying the voltage. You see that, and they are increasing the slowly. You see what is happening. He is trying to apply the voltage, and he is heating it, the filament get heated up. You see inside the chamber slowly. So he is applying outside from the using the dimmer stat. You see is slowly heating, and here the filament gets red hot slowly. You see that, see it's getting red hot slowly, and you see that the filament is getting red hot, and then the material is getting evaporated. So that is how the thermal evaporation occurs in this case. So the atoms, you are using a physical method to evaporate a material. That's what you will see here, and then we'll move on. So no, but suppose if I want to do a iron and platinum as a alloy. So in that case, it's not very easy to evaporate simultaneously, because iron has one melting point, platinum has one another melting point. Suppose if I want to do high melting point materials, in that case thermal evaporation is not possible, because once the filament is used for deposition of one kind of material, it cannot be used for other case. And if I want to use alloys like iron platinum or nickel chromium, this kind of alloys, it's not possible to use use the thermal evaporation. In that case, people go for electron beam evaporation. So in the case of electron beam evaporation, what they do, so you generate an electronic beam here, electron beam here, and which is your bottom part is cooled with the water, so that there will not be contamination between the container and your powder. And they will evaporate the powder, and because this entire system is under the vacuum, assembly is under the vacuum, it is very easy to deposit a thin film. So alloys could be used without a dissociation of the constituents. It will be good for nitrates and oxides also. It's very good material. So we will see how the thermal evaporation takes place. Sorry, electron beam evaporation takes place. Yeah, so you can put n number of things simultaneously. the electron beam. That yellow part is the electron beam. So here we can simultaneously measure the thickness here. This is called the thickness monitor, where you will be able to measure the thickness, how much of thickness you could able to deposit. That is what you will see here, and we'll move on. So this is the simple way of representing the electron beam operation. So you can have a multiple sources here. Suppose if you want to do a multi-layer, first I want to do a nickel layer, and later I want to go with the iron layer. Later I want to go with the copper layer. It is possible. You can have multiple sources as I have shown you in the video, and you just focus the electron beam onto whatever source you have, and you will be able to get the deposition. Contamination is avoided here, and you will have a high melting point. Metals can be deposited, alloys can be deposited, but on the other hand, E-beam also has a some kind of a restrictions, like source to substrate distance is small, because the chamber will be smaller here, not much of this thing, and co-operation is always possible, but substrate loading and unloading, you will have a very less space to do that. You have to be careful in that. But another problem is that E-beam is a costly technique. However, it is very sophisticated technique to operate, but depending on your application, you may have to choose. You will choose the E-beam. The best method, and which is generally being used among the scientific community when it comes to PVD, is the sputtering. Sputtering technique is a very simple technique. I will explain the sputtering in a few minutes with a video, so that you will be able to understand. So this is the general, this is the target. For example, this is your barium titanate target. You want to deposit a barium titanate atoms onto the substrate. So this is my substrate, this is my target. Between these two, I will apply the potential. So this is what is called the cathode, and your target is called the anode here. So when I apply the potential between them and introduce the argon gas molecules here, so the moment I introduce the argon gas molecules, argon will become a Ar plus 2 electrons. So these Ar plus ions, which are positive, and your target is at a negative potential. So what happens? They will come and transfer their momentum to the target. This energy is sufficient to remove the atoms from the target, and these atoms are released and they will deposit onto the substrate, because this entire assembly is under the vacuum. This is what is the principle called the sputtering. In this case, you have a DC sputtering. If I have a metal, I don't need to go with very high powers, so I can do a DC sputtering. Then I will go with the RF. If I have insulators, it is very difficult to break the bonds. So instead of DC, I will use the RF power to break the bonds. So this is what you see here. So you apply the potential here, and what you are doing, there are gas molecules here. So this, let me show you the video, probably it will be clear. So this is the sputter coater inside. You see, you will be able to move the substrate to get a uniform deposition here. These are the different anodes here. You will see how the deposition is happening. You see, the gas molecules will be entering through in the chamber. See, and these gas molecules are getting ionized here. The Ar will become Ar plus and 2 electron minus. These plus ions are attracted towards the anode here, which are your target materials. So they are giving their energy and they are releasing the atoms from them. You see that Ar plus ions are giving their momentum to this anode or your target material, and they are released the atoms. These atoms are falling onto the substrate. And this ionization process is happening simultaneously. You see that Ar plus are attracted towards the negative potential, and they are giving their momentum and releasing the atoms. And you see that this is the your anode surface. They are giving the momentum. They are releasing the atoms. You see how the Ar plus ions are transferring the momentum and releasing the atoms. You see. This is what is called the sputtering technique. So in this case, it is very easy to deposit insulating materials, and varieties of composite materials is possible to do in the using the sputtering technique. So I'll move on. So here also you see that you can do a multiple sources here, or you can do a multi-layer deposition possible. See, these Ar plus ions are coming. These red ones are Ar plus ions. They are transferring their momentum and releasing the yellow atoms, and they are falling onto the substrate here. You see here the atoms are falling onto the substrate, both the cases. So this is your substrate here, and this is your target here. So the line of sight is better when there is an angle between them is about a 65 degree. Then the rate of deposition will be better, and you will have a uniform deposition possible. That is what happens in the case of a sputtering. So you can have a DC sputtering, you can have RF sputtering, and also they call the reactive magnetron sputtering. Why magnetron is used? The magnetic field will confine the electrons in the vicinity of the cathode or anode, target, so that this they will release the ions or the substrate material atoms, and they will fall onto the substrate. So that is how the deposition occurs. So magnetron, what it will do is it will facilitate the movement of electrons within the vicinity of the anode, so that the more ionization takes place. More ionization means more argon atoms. These argon atoms will release the anode atoms or the material what you want to deposit. They will fall onto the substrate to get a more uniform and thickness of the film. That is what is the basic difference. That way, sputtering is the most effective technique if you want to see. So here physical mechanism used here, ion bombardment is used, momentum transfer is the main thing. In the case of evaporation, you have a very low kinetic energy, but in this case, you have very high kinetic energy. And here, you see that high evaporation source purities are possible, but in the case, since you are introducing gases, there may be slightly less purity, but the adhesion is much better in the case of sputtering compared to the thin film. PVD physical vapor deposition technique or thermal evaporation technique. And you will see here what are the qualities here. You will see that low gas incorporation, maybe some gas is there in the film, but still that doesn't matter. And grain size generally larger for sputtered film, larger than for sputtered film in this case. But here you see good adhesion is there, and you will have a very good grain growth also coming. Here you may have a fewer grain orientations, but here you may have a multiple grain orientations possible. This is the basic difference between sputtering and evaporation overall, if you want to look at. And I'll move on here, and processing parameters you can play a lot of them. The next technique is called the ion beam sputtering, as I told you. What is the difference between the sputtering and the ion beam sputtering here? In the case of sputtering, you are creating the ions between the substrate and the target. But in the case of ion beam sputtering, you create the ions in a source and bring them, and these ions will straight away hit your target and make the deposition. That is the only difference between the ion beam sputtering and the normal sputtering. Maybe I will show you a difference in the video. Maybe I have a video. So that is the only major difference between the sputtering and ion beam sputtering. I will move on because the time is less. And another is molecular beam epitaxy. So what is the molecular beam epitaxy? I will just introduce you here. So you see in the what is happening in the molecular beam epitaxy, the system is a complex system where you will be able to do a multiple depositions simultaneously. That is what happens here. So in this case, you can have a variety of films deposition possible. Here you see these are all different sources of materials, and you are introducing a substrate to be deposited into the chamber. So this is called the load lock chamber. So you will not expose this system always to the atmosphere, because this is always at a ultra high pure, ultra high vacuum. The vacuum level is about always 10 power minus 9 minimum. That's where you will use the load lock chamber. That means you will introduce your substrate into the chamber before that. That is what is called the load lock chamber. And then that you will transfer into your main chamber in the, you are sending it to the main chamber, that substrate, because the load lock is just open for a moment and your substrate will go and it will lock it immediately. So that your chamber is always at a high temperature, high pressures, ultra low pressures, and your substrate is here. These are all different materials that are possible. You will heat the atoms, like in the case of thermal evaporation. You will heat them, and you can also send the gas if you want to have oxide films here, and you will see that you are evaporating from the source and the atoms are falling onto the substrate. Here, you will be able to simultaneously do the XRD, you will be able to measure the thickness, you will be able to measure the film growth simultaneously in the case of a molecular beam epitaxy, because the film growth is very carefully controlled in the case of a that is what is the advantage here. So you see here your substrate, you will have one type of atoms and next another type of atoms. That way the growth is possible. See here you are depositing a next type of a material in this case. So like that you will be able to do a very precise growth in the case of a molecular beam epitaxy, and you will be able to simultaneously understand the grain growth characteristics. You will be able to measure the thickness, you will be able to take the microstructure, and many other properties you will be able to do. Of course, this is a very high cost and sophisticated facility. And another one is the laser ablation, where if you want to have a stoichiometry of the film very precise, then you will go with the pulsar laser deposition. How the pulsar laser deposition takes place, maybe I will show you the video here, how the laser deposition occurs here. So here your laser is focusing onto the target material. This is the material I want to deposit. The laser beam coming and evaporating at the surface of the material target, and these atoms are falling onto the substrate. That is how the laser deposition, laser ablation occurs in this case, where the stoichiometry is very crucial here. So this will not dissociate the material, but it will keep the material as it is, and then it will try to deposit the material onto the substrate. That is how the pulsar laser deposition comes into the picture. Okay, so these are all different comparisons that we can see. Maybe I will leave you this presentation with you, so you may watch and read. Of course, some of the videos that we have made in our laboratory also, I will try to give you these videos to your coordinator. He may give you the presentation to go for elaborative understanding. And if you at any point of time, if you have any queries, you are free to contact me. My email addresses are all, just you type my name, you will find all my details there. You can communicate. In future, if you want to do some collaborative research, you want to do some deposition, we have PLD, we have sputtering, we have thermal evaporation in our laboratory. If you want to deposit some of them, you may free to do so. So I think with this, I will stop here. If you have any queries, I would like to answer some. Thank you. I'm open for questions if you wish to have.
Yeah. Thank you, sir. Thank you very much. Now it is the time for queries. If anybody has any questions related to this expert lecture, you please ask, or you can post it in the chat box so that sir can answer your questions.
At any point of time, later time also, if you have any queries, you are free to contact me. Whatever possible, we'll try to help you.
Okay, sir. I hope everybody understood the session well. So that is why we are not asking questions, it seems. So no problem. Sir is available always. We can visit IIT Guwahati website and we can find out Sir's contact details. And we can be in touch with him if you need any kind of help related to the field of research in this particular novel materials, nanomaterials, nanocomposites, etc. So, sir will always be available to help. So, thank you, sir, once again for taking this nice session. The participants have given their valuable feedback also for this session. The session is very nice and very clear and super like that. So, thank you, sir, once again for taking this informative session. So now
Thank you.
we will start our second session at 12:15. The second session will be taken by Dr. Aroke Kumar sir. Is from NIT Warangal. So he will be joining at 12:15. So now from 12 to 12:15, we will take a little break. Those who want to be in the live, this meeting is still live only. So if you want to be here, you can don't quit the session. Don't quit the session, but you can stay here and take some break, and you can come back again and participate in the second session. So that will be also a very informative session. What are the quality techniques or tools that we use to make the novel materials in various manufacturing process? That will be the session. So experts sir will be from NIT Warangal. So I hope you will be participating in that session also.